Welcome to today's lecture in Economics of Innovation. Before I start, I want just to draw your attention to a small change in our schedule. I just go to StudIP and you see here our Ablaufplan, our schedule. Today is the 20th and we will discuss uncertainty and R&D patent races and adoption and diffusion. But just note there won't be a lecture on Thursday, the 1st of July. The point is simply, or it's twofold. First of all, we will need more time probably for these case studies, which we will discuss on July 8th. So be prepared that this lecture takes more like 3 rather than hours, rather than 90 minutes. And as you might notice, all of our streams from the previous year typically take quite long. Today's, for instance, is 1 hour 38 minutes, and that is means that we will be able to cover all of the previous topics up to the 24th. So in particular here you see we have both topics, two-sided markets and platforms, and innovation and antitrust policy. So no lecture on the 1st of July. I gave you also some explanation here, and just for your information. Okay, so that's what I wanted to tell you up front. Now I just want to start with the lecture. No subtitles today because for whatever reason Google produced German subtitles, and again I will also as always run the lecture or the stream at 125% of the speed. Okay, if there are any questions, just tell me in Webex. Welcome back to our Economics of Innovation course. Last week we started our discussion of uncertainty and R&D and we're focusing on patent races. Actually, uncertainty is a feature related to R&D processes usually, and we have two respects in which uncertainty is important. First of all, it's of course technological uncertainty. You never know how long it takes to come up with an innovation or what the inventive step will be of this innovation, how much better it is compared to other existing technology and so on. And on top of that, you get this market uncertainty. You never know whether you are first. If there are several companies in the same field, the problem is you have to be the first in order to get awarded a patent, and then it's often the case that the winner takes all. So two dimensions in which we have uncertainty, and this is what makes R&D first risky, and second, of course, something which might turn out to not be profitable. We already dealt with the question, how does competition, R&D competition, look like in such a situation? We had a very simple setup where just the firms were thinking about investing in an R&D project or in R&D laboratory, which had a certain probability, like the probability alpha leads to a research success. And we also came up with some results concerning the social welfare or social optimal level of R&D. However, we used more or less, in a sense, as a welfare measure, the measure of joint profit maximization. And we saw that with this respect, firms typically invest too much in terms of R&D, even though what we also saw, that is a third point here, that R&D competition will speed up innovation, and we expect innovation to come up earlier. Today we want to start with the question whether firms will choose projects which are too risky, and then we move back to our patent races and do a slightly more elaborate kind of analysis than what we did last time. And in this analysis, we just do not view R&D as a binary process where you either set up an R&D laboratory or you don't, but as a process in which you choose your level of R&D activity. So meaning that if you invest a little bit more in R&D, it's more likely that you come up with R&D success, or it's more likely that you're the first to come up with an innovation. But first of all, I want to start with R&D projects, and as always, just send me a message in the chat if there are any problems with the live stream. Okay, the question is here, once we have risky projects, the question is whether firms will choose projects which are too risky in a certain respect from a social point of view, from the point of view of joint profit maximization and so on. What I mean by risky should come up clear when I present you this example. So just suppose you have two different technologies which are available and they have the same expected date of discovery, but they have different variances. And what we will see, or what I want to show, this is based actually on a textbook chapter by Georg in his book on industrial organization. We will see that competition implies a preference for risky project, and that has got something to do with the winner-takes-all character of patent races, which urges R&D competitors to pick technology that are too risky in a sense and that involve more variance than is socially optimal. Socially optimal here in the sense of joint profit maximization, because you have a negative externality you do not take into account once you choose a rather risky project, because that reduces the probability that your rival will be the winner. So we will also have a problem in assignment set here, and as I told you, it goes back to an example in Jean Tirol's book. Okay, so what is our example here? Just let me see that. So our example here has two firms and two projects, or you might call them two R&D approaches. And we have a very simple setup. There's a 4-year time horizon, and perhaps I show you already the next few bullet points here. And here you see the 4-year time horizon. After 4 years, the word ends here. It's like after 4 years, a new technology will appear, and even though you're in a market right now, you will be driven out from this market because some new technology becomes available. And the point is here, we don't assume discounting for reasons of simplicity. It just would make that riskier projects will be even more preferred. Now, the point is here, what we assume is that project one is a safe technology in a sense. What does this mean? Now, so you see, you can have you have this 4-year time horizon, and this project one gives you a discovery in the interval from 1 year to 2 years. Project 2 is a more risky technology. It gives you a chance also to have right from the beginning a success rate is from 0, but it might also take you 3 years. Okay, uniform distribution on these 3 years. And now, of course, the profit from discovery is something like V, which is a value of your innovation. And now the 4 minus T simply means if you're successful after 2 years, you earn this profit V for 2 years. If you're successful right now, you earn the profit for 4 years. If you're successful only after 3 years, you will earn the profit only for 1 year. So this should be clear, hopefully. So you have these two technologies, and we need some notation. Here we describe by pi1 ij, we describe by pi1 ij, we describe the profit of firm 1 if firm 1 chooses project I and firm 2 chooses project J. So if we have pi1 1, 2, we know that firm 1 chooses project 1 and firm 2 chooses project 2. Okay, that's what we are doing. The two projects, it should be clear. Perhaps I should also tell you about the expected date of discovery. So both, that's what I told you on the last slide, both have the same expected date of discovery, which is in each case 1.5 years. So in a sense, both technologies have the same expected date of discovery, therefore the same expected profit, and but it's quite obvious that project 2 is the more risky one. So if we had a monopolist who can decide about the two projects, the monopolist, if the monopolist is risk neutral, he or she would be indifferent between the two projects, given the costs of the two projects are the same. If one of the projects is highly or slightly more costly, more expensive, it would choose the other project. Okay, that's what we are doing. Before we move on, just YouTube keeps telling me that I have a bad connection. So if there are any problem with the stream, just tell me in WebEx, please. Okay, we move on, and so here's just a very short digression into how you calculate expected profits, or actually an expected value, if you have a continuous random variable and some density function fx. Our random variable actually is nothing else than our profit variable, and hopefully that's what you know from your math or statistics class. It's simply this integral from -infinity to infinity, where you multiply the value of the random variable with the value of the density, and you get the expected value. In the case of the uniform distribution, which is particularly easy because the density is very straightforward. It's 1 over the upper limit of integration minus the lower limit of integration. Just remember we had this two projects. The one was in the interval from 1 to 2. So it would be 1 over 2 minus 1. The density in this case would be just 1. In the case in which we have, actually I think I have even written it down here so I don't have to write it down by hand. So the density of project is 1. The density of project 2 is 1/3 because here the upper limit is 3 and the lower limit is 0. Okay, and if only one firm invests in R&D, the random variable x is just equal to this profit, and the profit is just v4 minus t. Okay, that's what we have. We will do that now in many different cases, so it should be rather clear after the next slide. And here, just a case in which we have only a single firm investing. Firm 2 has no project. So if it chooses the safe project, you see it's from 1 to 2. Oh, actually, probably it's always bad when I write like this here. The density is 1. Okay, this would be our fx. And here, this is then simply our random variable x. And now, this is then a straightforward integral. Here, the t is just I don't know where it's integrand. It would be in German. The variable over which you integrate, and it's straightforward to calculate that this integral gives you a value of 2.5v, which is obvious anyway because you know that the expected date of discovery is 1.5, v is 4 minus t, and if the expected date of discovery is 1.5, we are left with 2.5. Okay, and the expected date of or the expected profit of project 2 is exactly the same. However, it's put slightly different because now our domain of the density function is from 0 to 3. Okay. Now, of course, it's you always could put it in terms of minus infinity to infinity, but from minus infinity to 0, the density would be 0, and from 3 to infinity, it will also be 0. Okay. So it should be clear. Now here you get the 3, and that's just from our 1/3 from our density times again our random variable, which is just the profit here. Okay, and again, the expected value, as I told you, was 1.5 of the expected date of discovery, so it's 2.5. At this moment, it should be clear that both projects have the same expected profit in the case in which we have only one firm investing into the project, and that project 2 is, in a sense, the more risky as it exhibits a higher variance. Okay? Should be clear. We will now play around with many of these examples, and you will see many expected values be derived. Okay, first of all, we start again with firm 1. If firm 1 chooses the safe project, and firm 2 also chooses the safe project. Now, again, it's clear you only have a positive density on 1 to 2, and of course I could add here somewhere a 1 times, okay, could add that here. I get here the value if you are first. However, now we have the second term here, this 2 minus t. What does this 2 minus t mean? Now, you only get the profit if you're the first. But now the second firm also has the same project. And now we have to take into account the probability with which you are first. Now, what is the probability that the other has invented at some date, say at the point t equal 1? As it starts only at t equal to 1, this project, the probability will be 0. Okay, at time t, the probability that it is successful, has been successful by that time, of course, is 1. So the probability that it was not successful is 0. So that's what you get in more formal terms. And I think that I have depicted that in some detail in the notes. The cumulative distribution function of having made an innovation by time x, fx, is just x. Is just x minus 1. X minus 1. Okay, so now the probability that someone with this distribution function has made a innovation by, say, time 1.5 is just 0.5. By time 2 it's 1, by time 1 it's 0. And of course we are interested here in a situation in which I earn this profit, and I only earn this profit if my rival is not successful, and the probability that not success. So, well, if I try to write, I always prop not successful would be just 1 minus fx. Okay, And now, of course, 1 minus fx immediately gives us this 2 here. If fx is the above thing here, you get just 1 minus x minus or plus 1. So it would be 2 minus x. And this is exactly what I wrote here. Okay? That's important, but it should be clear. And it's such a with the uniform distribution, it's just straightforward. Yeah, but now we already have it. We have this integral, and now, of course, just check it whether you come up with the same solution, but it's now 4 over 3 times v. Remember, in the previous case, it was higher because it was 2.5 times v. Now, of course, the problem is that it's not clear if you choose this research project that you are really the first or whether your rival is the first. And here, again, our 2 minus t is just a probability that the rival is not first, that it hasn't made the innovation by the time you innovate. Okay? So that's it, and now we can just move on. I erase this part here to look into the next case, where we have again our company 1, which now chooses the risky technology when firm 2 chooses the safe technology. And of course now we have also this interval from 0 to 1. What happens between 0 and 1? Yeah, we get this 1/3. Why do we get this? Now, remember, this is a density because we are in the interval from 0 to 3, and with uniform distribution, this is just our density. This is our f of x. Now, what is the probability that your rival is successful in this interval? Of course, it's 0. The probability that it's successful is 0, meaning that the probability that the rival is not successful is, I just could add times 1. The probability that the rival is not successful is 1. So if you're successful in this range, you're certain to get this. But of course, with a certain probability, you do not end up, and actually it's 1/3, of course, you do not end up in this interval, but you end up in the interval from 1 to 2. This would be this interval then. And here actually you have exactly the same expression as you had here, because in this interval the probability that your rival has not been successful is 2 minus t. Of course, what is missing here is actually plus integral from 2 to 3 and so on. But the point is, what is the probability that the rival was not successful? It's 0. Okay, that's why I dropped this point. Okay, so here you have also the chance that you're successful only after time 2, but then it's clear that you won't be the first to innovate. Yeah, now this is a bit longer, this expression, but still just 2 very simple integrals, and if you throw it into Mathematica, it's just what you get here. Okay, and the interesting thing is here, of course, we want to compare, given, or what would we do? Given the rival chooses the safe technology, would I choose the safe technology 1, or would I choose the risky technology 2? And of course, that depends on how profitable 1 is compared to 2. And what I see here is that 4 over 3 times v is smaller than 29 over, or actually just multiply everything by 6 here, you would get 24 over 18. Of course, is smaller than 29 over 18. Okay, so this is this would be just equal to pi 1, 1, 1. So the point is that the profit from choosing the safe technology is lower than the profit from choosing the risky technology, given the rival chooses the safe technology. Okay. Of course, we didn't take into account here any cost differences. Just for the moment, assume that the cost of the 2 research projects are the same. Now, of course, we also have to do that for the other case if the rival chooses the risky technology. And what you see, if the rival chooses the risky technology, and I also choose the risky technology, both of us are active, actually can have the innovation in the whole range from 0 to 3. And now again, we get this profit. We get 1/3 here again from our density function. And again, we need to calculate our what we have up here, our cumulative distribution function. What is the probability that the rival was not successful by a certain time? And this is simply prop p not successful would simply, I don't know why I always get these points here, would simply be 3 minus t over 3. 1/3. And you immediately see that, of course, for 0, this should be the for 3 minus So yeah, now it works, okay. Or it would be 1 minus t third. And of course, if t is 0, the probability that the rival is not successful is 1. If t is equal to 3, the probability that the rival is not successful is 0. This probability, or if we are at 1.5, the probability that a rival is not successful is 1/2. Okay, and you can calculate or derive that just the same way as we did previously. The only difference now is that the x would not, that this fx would not be from x minus 1, but it would be x minus 3 over 3. Okay, that's what we have here. And I have in some length also described or explained that in the notes as well. But it should be straightforward, and it's rather intuitive. And once you get that, you get here 1.5 times v. Okay, and hopefully all these terms are clear right now. Here it should also be clear if your rival chooses the risky technology and you choose the safe technology. Okay, of course you can only be successful in this part. Here the 1/3 comes from this probability of, perhaps I should better write it here, because this 1/3 comes from the probability of the rival not being successful, and yeah, you have a density of 1, that's why the 1 is not here, and you get this 23v over 18, and again 23 over 18 is smaller than, expand that by 9, than 27 over 18. Okay, now we already have this important result here. Actually, both in a Nash equilibrium, given the cost of the projects are identical, it's always optimal to choose the risky project. Okay, that's what you get here. Suppose your rival chooses the safe one, that is, we are above here. Okay, we are above here. Then choosing the safe technology gives you a lower profit than choosing the risky technology. And also in the case if the rival chooses the risky project, is again better for you to choose the risky project. Okay, that's our important result here. And both firms will choose the risky project. Okay, now what has that got to do with private and social optimality of the projects? What would a social planner do? Now, the point is here, as it's clear that the profit from choosing the risky project is higher than from choosing the safe project, you can construct a range in which, even though the costs of the risky projects are higher, firms still choose a risky project because the profit associated with that is higher. Okay. And here is just what you get, this cost difference. This cost difference, if this cost difference is smaller than this difference in profits, firms choosing the risky technology is the equilibrium outcome. Okay, and what is clear, if you have any cost difference here like this, if the cost of the risky project is higher, a monopolist would always choose the safe project. Okay, and now you can just calculate the range in which you get the risky project, and here what I wrote down here is that this is a situation in which the total profit, or the profit from both having the risky technology, this profit difference to both using the safe technology is just v over 6, which is v over 18, and this is what is here. So in this interval, okay, both firms will choose the risky technology, even though the joint profit or the joint profits would be maximized if both firms choose the safe technology. Okay, you see here the cost difference is higher than the profit difference here, up here, okay, and that means that it's really bad in a sense for both of them, but here we just have a prisoner's dilemma and negative externalities. Yeah, I think that's about what. Okay, I will make a short break here. Before that, I will show you, perhaps you are really somehow frustrated or overwhelmed by all of these integrals. I will just show you that if the assignment for next week, what you will see here is that it's actually a rather simple kind of question we ask here, and most, or by now, students always have been in a sense a bit confused because it's too easy. They always want to do it in terms of integrals, but this, as you will see, this problem is much easier to do. But anyway, I just want to move to WebEx right now for a short break and ask for questions. What I wanted to tell you about this riskiness example, I think we could play around here a lot further, because if you have a higher cost difference being higher than this 4 V over 18, but lower than 5 V over 18, asymmetric equilibria would exist. Asymmetric equilibria in a sense, if one of the two firms has, or if one of the two firms chooses a risky technology, the other firm chooses the safe technology, and vice versa. Okay? Hopefully this is clear here. We will have a nice, I think, problem in our assignments. And as you will see, typically students think that the problem is much more complex than it actually is. You will see that it's rather straightforward to calculate. I stop here and make a brief break for any questions you might. So you saw it was a bit early, but anyway, we just move on right now. We move on now with our patent races. And remember, I already told you in the introduction that in the first example we looked into, we had the situation where the firm just had the decision whether to set up an R&D laboratory or not. And if it set up an R&D laboratory, it got a probability alpha that it is successful. What we want to do now is we want to look into the case where the firm chooses the R&D intensity. And by choosing a higher R&D intensity, that is a higher investment in R&D, a higher expenditure on R&D, it gets a higher probability that it is first. As always, we start with a value of the patent, and then Hj is the R&D expenditures of one of these n firms here. And what we assume here, that firm J's probability of making the discovery first is defined as follows. This example or this model goes back to Helmut Bester, which he wrote that up in his textbook on industrial organization. And once you compare these with the more complex kind of patent race literature, you see it's really ingenious how he did that, because he modeled that in a rather accessible way and allows to draw some conclusions from rather simple setup. Okay, so what does all this mean? This pi j is a probability. This pi j is a probability. It depends on how much our firm J invests in R&D and on how much the other firms invest in R&D. And it depends on some factor alpha, which determines how complicated it is to reach a success anyway. I will, in the following slides, I will explain you that in more detail. The important point is here that increasing your own R&D expenditure relative to your rivals increases your probability of success. Okay, that's what we show here. And actually, if alpha is 0, we actually have a contest. Okay, context means just like a tournament. So and everyone, if everyone invests, if you have 2 people and everyone invests the same, each one has a probability of 1/2 to win the contest. If you look into the Bundesliga, I just read in the Süddeutsche Zeitung that the point why Bavaria is going to, Bayern Munich is going to be Deutscher Meister is due to the 750 million they spend each year compared to the 500 million Borussia Dortmund only spends, and the other thing. So in terms of the Bundesliga, alpha of course is 0, because one of these 18 clubs which are a member of the Bundesliga will become the Deutscher Meister. Okay, he will become the German champion. And of course here, if you look into Paderborn or Union Berlin, which spent, I don't know, 60 or 70 million, and then you look into Bayern Munich, which spent 750 million. So what is clear, suppose a total expenditure of 3 billion, so the 750 would give a chance to Bayern München of winning the Bundesliga of 1/4, and then 1/6 to Borussia Dortmund, and so on. Okay, that's how it works. Of course, Bayern München will always become Deutscher Meister, as you learned, and as I'm a fan of Bayern Munich, so it's clear. And I don't know whether money buys, but anyway, hopefully you got the point. Okay, so this is very important, and this was a very good forecast, as you see, because Bayern Munich became German champion this year as well. So now suppose we have some alpha, and I think we have here our definition. If we have only 2 firms, and one of the firms spends these 10 million, okay, what is your probability to be successful or to be first? So the important point is, it's not only that you're successful in the research, but that you are first. And here the probability, if you also spend, say, 10 million, it depends on the alpha. If alpha is 10, you will see it's just 1/3. Okay, 10 over 10 plus 20 is 10 over 30, it's 1/3. So this is a probability. And the important point, or there are 2 important points about these 2 curves. The first one is that they are concave. That means you have diminishing returns to R&D. even if Bayern spends 10 billion, it's not clear that since the other also spend, there's still a small chance that you're not successful. Okay, this is the diminishing part. And what you see, if alpha increases, it reduces your probability of success. Okay, because then the probability increases that no one is successful. That's what's depicted on the next slide here. Here I also wrote down the probability that no one is successful. Just think in terms of our COVID-19 vaccines. You have two firms investing, but still, if they invest a lot, the probability to be successful will increase. Okay, but still there's a probability that they don't find this vaccine. And pretty much here you see, this is for alpha 10. Here you again have our case of 1/3. So each of the two firms has a probability of 1/3 to be successful. And with a probability of 1/3, no one comes up with this innovation. Okay, and what we look into here is that both firms at the same time increase their R&D expenditure. Okay, and what you see here, if we had a contest, if both firms increase their expenditure in the same amount, the probability always stays the same. They always have a probability of 1/2 to be successful. So in the US, you have a salary cap for all the players in the NFL and in the NBA, and that just means that's just like a cartel. Anyway, this is another topic, but. So you cannot pay more than a certain amount of money. And of course, if you reduce that by half, you would just keep the probabilities unchanged. And if you double it, you also keep the probability unchanged. Okay. And what you see here, of course, if these firms increase their R&D expenditure, it just gets more likely that one of the firm has or makes the innovation, gets less likely that no one is successful. That's why this red line approaches 0. Hopefully that's clear right now. Here again, our description. And you see again, the important point being here, the concavity. The alpha is important. Yeah, that's pretty much it. And once we have that, we can set up our profit maximization problem. Okay, and as always, we just maximize profit with capital pi here. And again, now, of course, it's expected profit because it's uncertain. You decide on how much to invest in terms of R&D expenditure H. Okay, and your probability, whether you are, or of course, pi j is a probability that you are first, and your probability depends on your own R&D expenditure, which would be this, and on the R&D expenditures of all your rival. And of course, you have costs. And now, using our functional form here for the probability, we just come up with this expression. Okay, and of course, the large part of this somehow I think I'm missing a minus hj here. Okay, I just forgot it. Okay, now here we derive the first order condition, very straightforward. Of course, the point is here, if we take a derivative with respect to hj, we have hj both in a numerator as well as in a denominator, so we have to apply product rule, or is it quotient rule in English? I don't know. And here we take the derivative with respect to expenditure, we get 1, because of course if we spend €1 more on R&D expenditure, our profit will go down by €1. And here we have this increasing part. If we spend more on R&D, we just increase our probability to be first. Here the second part actually this negative part accounts for the diminishing rate of R&D expenditure, for the diminishing returns to R&D expenditure that was due to this concavity of the curve. And now you see it's somehow an ugly expression if you put that on a common denominator, but still it's okay. Okay, but what you don't like here is all these different HIs, HJs, and so on. Hopefully you are familiar with this kind of summation here. You just sum up from I equal to 1 to n, but do not take into account the HJ here. Okay, because that cancels out. Okay, now, of course, this looks terrible, but what we are looking for, all of these n firms are alike, so we are looking for a symmetric equilibrium, and then it turns out to be much nicer, because this sum over all hi will just be n minus 1 times h, where h is our optimum, and here we have actually the same. Okay, so that's once we solve for a symmetric equilibrium, it looks rather straightforward, and we get what we might call an implicit function, which determines then our h here. Okay, in this case, we can even calculate here. I solved for v on the one hand side and for the other term on the other side, and this is just a function of h star of alpha and of n. And here we can even calculate or get a closed form solution for the h, but that looks ugly. So what we see here somehow is, or what we are interested in, is of course some comparative statics. So how does each firm's R&D expenditure depend on important exogenous parameters like what is the value of the patent, what is the number of competitors, and how complicated is it to come up with a research success which is measured here by alpha. And as this is complicated, I just draw some lines here where I use just some simulation. Okay. What you see here, and here is also why you see why I put it in this term here, or actually I think best I did it like this. And here's, you can just easily plot this line here, and or it's not a straight line, but it's here this curve. And what you have here is the optimal h, and here is the optimal, or here's the given v. Here I assume that v is 10. Suppose, and the point is here the black line is a v, and of course our optimal h is determined by the intersection here. So I think this is about 2.5. So if n, the number of competitors, is equal to 2, if alpha is equal to 1, and if v is equal to 10, our optimal R&D expenditure is 2.5 or 2.5 million. Okay. Now, what we are interested in, first of all, of course, we now have shown that an optimal R&D expenditure exists. Okay, you don't invest nothing. You will invest something. You have the probability of being first, even though it's uncertain what you get. You get something, or you have a chance to earn something, so you invest something. Now, of course, what we are interested in, how much you invest change if you get more rivals, if you get. Here you have the red line has 3 rivals rather than 2. And now what you see is, if you get an additional rival, the optimal h will be a smaller one. Okay, that sounds like plausible. If you have more rivals, each one invests in R&D, that just reduces your chance from being the first, and therefore you will invest less in R&D. The interesting thing, however, is that aggregate spending on R&D will increase, and therefore the probability that no one makes innovation decreases. Okay, from a viewpoint of society, it seems to be good, because you get a higher R&D expenditure and therefore a higher chance to get some innovation at all. Because here what you see, with 2 firms, each one choose about 2.5 million, so we would get an aggregate expenditure of 5 million. With 3 firms, each firm uses or has something like 2 or 2.1, and 3 times 2 or 2.1 is above or about 6 million, so we spend more on R&D. Now, finally, the blue line, here we compare, in both cases, in the case of the red line and of the blue line, we have 3 firms being active. And now what we increase is this alpha, that is, we make R&D more complicated, or we make it less likely that it's successful. And of course, that's obvious. If R&D gets harder, your chance of being successful goes down, and therefore, if alpha gets harder, firms will reduce their R&D expenditure. Of course, what is obvious here, if you increase the patent value, firms will invest more in R&D. Okay, that's what we immediately saw here. So you get a much higher R&D expenditure, irrespective of how complicated R&D is and how many competitors you face. I think I now gave you all the results already on the previous page. So first of all, I showed you that there exists some optimal R&D expenditure, which is strictly greater than 0. So we invest in R&D. You see that R&D expenditure of each firm decreases if the number of firms increases. There are some models in which this does not hold. In particular, I think the Lee-Wild model, if we have time, if time allows, I will briefly mention that. This model has a slightly different setup in which we don't have upfront payments, but per period payments. I'm getting back to that. And what I also showed you, that the industry R&D expenditure n times h increases if the number of firms increases, and an increase in competition therefore reduces the expected date of discovery. Okay, again, competition is good in this respect, even though each individual firm invests less. And of course, that's what I told you. If the value of the patent increases, firms invest more in R&D. What we see here again, that firms might overinvest in R&D from the viewpoint of a social planner. But here again, there's a discussion between Lee and Wild, and two important contributions from the early literature some 40 years ago on patent races. Okay, brief break here, just asking for questions. Okay, we move on. We will have to discuss later on whether Germany will become football champion or European champion in football. I don't know how this kind of contest works, and at least Jogi Löw now put on his squad very expensive players like Mats Hummels and Thomas Müller. Okay, we'll move on. Okay, now once we have this introduced, this nice way how Bester formulates this probability of being first, we can revisit our discussion. We had to remember the sleeping patterns and the question whether an incumbent or an entrant will always be the one who bids most for a new technology, which is something like developed by some independent laboratory. We saw the depressing result there that you always have persistence of monopoly, and that a monopolist, in a sense, can use the patent law to keep on her position. Now, we introduce uncertainty in this situation, and you will see that we might get a slightly different result here. Okay, again, same setup as, hopefully you remember that was our after the arrow model, we discussed that. So we have some new technology allowing production at lower cost. Currently, we have some monopolists. Pi I would be the expected profit of the incumbent, and pi E would be the expected profit of the entrant. And here you see, looks a bit ugly, but it should be obvious in a second. First of all, your expected profit depends on your own R&D expenditure and on your rival's R&D expenditure. So the entrant's R&D expenditure, HE. Okay, so this is a profit of the incumbent. Now, if the incumbent invests HI and the entrant invests HE, the probability that the incumbent is first is this here, okay? And with this probability, the incumbent is first, and it gets this innovation K lower bar. So if it gets this innovation, of course, it's a monopolist using the new technology. With probability pi E, the entrant is first, and in that situation, the monopolist is second, has the high cost, is a high cost monopolist, and gets this profit, okay? However, there is a third possibility now. This third possibility was not in the Gilbert-Newbery model, okay? Because it was clear either I get the new technology because it's already developed by an independent laboratory, or if I don't buy it, my rival will buy it. But now, if I have uncertainty, if I have to develop this vaccine on my own, either I get it, that was this the first part, or my rival gets it, or no one is successful, and this is this probability. Okay, with some probability, no one of the two is successful, and I still keep my monopoly position based on the old technology. Okay, minus of course my R&D cost. Should be clear, hopefully, even though I make all these strange red lines here. Of course, it's always much easier to look into the entrance expected profit. And here what we see is, again, we have the pi E, the probability that the entrant is first. And if the entrant is first, she obtains the duopoly profit with the low cost. If it's a low cost firm, minus HE, of course, it doesn't get anything if she doesn't get anything if she's not the first innovator. Okay, so what can we tell now? Actually, what we can show immediately is that for drastic innovation, the entrant will always invest more in R&D than the rival. For non-drastic innovations, the reverse might hold, because for non-drastic innovation, this duopoly profit might be rather low, okay? Whereas the monopoly profit, again, from monopolists, for the monopolists might be rather high. For the non-drastic innovations, it's just a standard Gilbert-Newbery rational. But here for drastic innovations, it's the opposite, and that's, you don't have to, I will explain that on the next slide. Okay, because how do profit functions look like in the case of drastic innovations? How do they look like in the case of drastic innovations? Now, in the case of drastic innovations, there is no duopoly profit. Okay, so that is either I'm the monopolist. If I'm first, I keep my monopoly position as an incumbent, and I have the new new lower cost, lower production cost, or no one is successful. In this case, I still am the monopolist with the old technology. It looks slightly different here for the entrant, because the entrant then, of course, gets the monopoly position. It's a drastic innovation, okay, minus HI. But what you see here immediately, if you take the derivative, if you look into the first order condition, Actually, I probably should have written that up. If you increase your HI, of course, you increase the probability of being first, but at the same time, and here you have the negative sign, okay? Here you have the negative sign. Here you have the negative sign, and what that means is you increase the probability to be first and to have the innovation, but you also increase the probability that there is an innovation, and that is you cannibalize your own profit, which you got, or which you get if no one is successful, okay? And due to this negative effect here, it's clear, which is not absent of, not present, of course, for the entrant. You will choose a lower level of HI. Okay. Again, this is just this minus here. You could just rearrange it. You could just write this as here pi I. You could rearrange it, write it as pi I HI HE times pi mon Q lower bar minus pi mon Q. Okay, of course not Q. Okay, so that's the point. That's what you see here. The expected profit is greater for the entrant for drastic innovation. So that's a very interesting result, I think, because it just tells you drastic innovations are more likely to be introduced by entrants if there is sufficient uncertainty. Okay, perhaps it's a coincidence, but which country is leading in the development of electric cars? It's not Volkswagen, it's not BMW, it's not Daimler. They all had their nice profits from selling fossil fuels cars, okay, combustion engine cars. But it was Tesla who developed this new because they had to win most. And probably electric cars are rather close to a drastic innovation. Of course, if it holds for a drastic innovation, it will by continuity also hold for almost drastic innovation. So even though you get some duopoly profit, it will still hold. But as I told you, it might not hold if these are very small innovations. And actually, there have been interesting empirical studies. One paper by Dirk Czarnicki and formerly with the ZDW, now at Leuven, and Cornelius Kraft, who I think was in Dortmund. And they did an empirical test of asymmetric models on innovative activity, and they asked, is it Gilbert Newberry who are right, that it's always the incumbent, or is it more that this goes back to a paper by Jennifer Rain-Ganom in the 80s? Is it more like Jennifer Rain-Ganom? And their result was that Rain-Ganom appears to be empirically more relevant. It's more likely that drastic innovations, particularly large innovations, are introduced by entrants rather than by incumbents. Okay, so actually that. Okay, just asking for. I will just ask for questions. That was pretty much about what I wanted to tell you about patent races. When I started my career in the 80s, patent races were everywhere, published in each issue of each journal, and they had very different versions of this. We had fixed numbers of firms versus a free entry number of firms. We had deterministic patent race models and stochastic models. We had models with simultaneous decisions and sequential decisions. We had identical and heterogeneous firms. We had upfront and current R&D expenditure. We had memory or memory-less races. We had winner takes all and positive profits, payoffs for some losers, perfect information about rivals' actions or imperfect information. I don't want to go into detail here. I just want to give you a very brief glimpse once you manage to or get across some of these models, that you get some idea how they look like, because here we actually talked about patent races but didn't model time explicitly, okay? And that's what is done in these models. If you have a deterministic model, it's actually an auction, then the date of innovation depends on R&D expenditure. You have n identical firms and you have the price of an innovator. And now if X determines your date of innovation, and it's a deterministic model, of course, you can immediately write down the payoff of the firms. If what is clear, and that's what I show you on the next page here with this T function here, numerical assumption here. Suppose if you invest 1 million euro, it will take you 100 years. If A is 100, it will take you 100 years until you come up with the innovation. If you invest 100 million euros, it takes you 1 year to come up with the innovation. Okay? And of course, if rivals invest more than you, you will come up with the innovation later and you don't get anything. If the rivals invest the same amount as you, all of them will come up with the innovation at the same time, and the assumption here is that they just share this value. If you invest more than the others, the point is that then you get Of course, you have to pay the investment, but you get here the value. Of course, this value is discounted. Okay? Just to give you a small illustration here, interesting actually always in terms of COVID-19, currently we are trying to speed up the process of the development of this vaccine. Okay, and what that means is if we want to have a very low time until we get it, we have to invest a lot in R&D. That's what we currently do. And that's what this model captures. And now, if only a single firm were to invest, its profit would look like this, okay? Depending on X, you see if a monopolist did that, because you have some R&D cost, you have the shape of this T function here, you just get some optimal, this is just the V was just here on the previous page, the value or the payoff of the firm. And what you see here is you get some maximum value. So if you were a monopolist, you would just choose a T of 3.82 and X, that's what's written in the notes, an X of 26. And zero profits you would get if X is 89, okay? And time T would be 1.18, okay? Now we have an auction. Okay, suppose you have 5 firms being active in this auction. Profit maximizing, if a single firm would be active, would be what? It would be to choose this X of 26. Okay, but what would if you invest 26? Yeah, what would the rival do? It invests slightly more because it then overtakes you and still gets a profit. But if your rival invests 27, you invest 28, and so on. And finally, where does this end? Yeah, only here once you make no profit. So if you invest, say here X of 89, your profit is 0. But the problem is, how much will your rival invest then? It will invest 0. But if your rival invests, how much will you invest? Actually only 26. But then our game starts from the very beginning again, and your rival will invest 27. So what's the story I'm telling you is that just the story that no Nash equilibrium in pure strategies exists in such a deterministic model. Okay, should be clear anyway, and this goes back to another paper of Dasgupta-Stiglitz. This is not the same paper we had in chapter 3, but a different paper on patent races. Okay, and you have then some sequential moves. If someone is first and the rivals can only move second, the first will always choose then an X of say equal to the zero profit condition. Okay. That's what we are doing. Here you get in your notes, you get many things, how you get from discrete discounting to continuous discounting. This is the part about the Rangana model. You also learn about the Poisson distribution. Unfortunately, I don't have the time, but the Poisson distribution is heavily used in this model. It's the so-called memory-less distribution. We have been discussing that again. And the final point I just want to mention to you is the Lurie and I think I'm at the right slide. So I just learned that it's really the advantage of doing that on YouTube, because you can, after the lecture, just go back and look up what I said. Okay. Now the point here, I was telling you about that our model has some upfront payment. Of course, in a static model, it doesn't make sense to distinguish between upfront and per period payment, because it's only one period, so it actually coincides. What you have here in terms of the upfront payment is just here some X. Okay, here you have your, what you see is actually, that's why what Helmut Bester did is so ingenious. It looks very similar to our model, okay, even though this is a model, a very complicated model in continuous time. Now here you have the upfront payment, and you have some R&D laboratory, invest in that, and this gives you then some expected value with some expected date of discovery. This was the Lurie model. In the Lee-Wild model, you don't have this upfront payment, but you have a per period payment. Okay, you can look that up later on. This is a huge difference because you pay every period. The question is which one is more realistic, or which one applies in which case. Do firms make huge upfront payments, and so they have to pay still, even though the rival already gets the vaccine? You still have your researchers here, and they still work on the vaccine, even though it's clear you don't get a patent. Now, you might think that Lee-Wild is more realistic because you just fire them then, but is it realistic that you can fire them? Okay, so here you see it's an important empirical question. But actually, that's I want to leave it at that. And before I turn to adoption and diffusion of new technology, I think you and I, we really have deserved a small break. Okay. Okay, some break here. Patent races is really hard stuff, and it was really rather productive stream of research in the 80s and 90s. My colleague from Tübingen, Manfred Stadler, did a lot on that, and I also made some attempts to come up these models. It was rather hard to, at that time, to solve these complicated models, but as you see, you get all these different slides which explain that in more detail. So once you get to such a model, just look into that. I now want to turn actually to another point where I did some research on my own. That's why I also have in the notes a quote from my RAND paper. It's about adoption and diffusion of new technology. What does that mean? Now, the point is, new technology, of course, if you have smartphones, if you have electric cars, you only realize the productivity and welfare enhancing powers of these new products if they're actually used by its potential users, okay? And therefore, it's rather important, this adoption and diffusion of new technology in order to get technical progress. And so the point is, why are we not just adopting all these nice new technologies? And again, we go back to Schumpeter, and that's a quote from his actually 1911 book on Theorie der wirtschaftlichen Entwicklung. This is just the English translation. And what he just mentions is that we see all around us in real life faulty ropes instead of steel horses, defective draft animals instead of show breeds, the most primitive hand labor instead of perfect machines. And what is really interesting, this quote goes on with, I just have to look it up, clumsy money economy instead of a check circulation, and so forth. So in Germany, we still pay cash. Might change with the Corona crisis, but we still pay cash even though you have something like Google Pay or Apple Pay and so on. Okay? So the point is, why is that so? And what Schumpeter moves on in his book is that the economic best and the technologically perfect need not, yet very often do diverge. And the point is, we diverge, okay? We have technological best, but still we do not use it. The question is that because of ignorance and indolence, as Schumpeter puts it, are people just too stupid? Actually, what Schumpeter said, it's even though these other methods, these old methods might be technologically inferior, they may still best fit the given economic conditions. Okay, that's the important point, and that's what I'm going to show you why that is so. Why it might be optimal not to adopt new technology immediately, and why we typically see or observe in the real world that adoption of new technology does not take place immediately by all agents, but it takes time. Okay, it takes time, and that means that it happens sequential rather than simultaneous. There are some early adopters, but there are rather late adopters as well. And it holds both for intra-firm adoption. Deutsche Bahn not only has very modern trains, but very old ones, and it is much holds even more for their whatever Stellwerke is in English. Okay, they even have these would be interlocking. I looked it up. Switching, these large switching. I don't know how you would translate that into English. From the times of Kaiser Wilhelm. Okay, it holds for intra-industry adoption, it holds for economy-wide adoption, and I will give you many examples right now. Or in many. So that's a typical shape, and I'm sure that you are well aware of that. This is a typically S-shaped diffusion curve. Yeah, it's just an S-shape here. Would be about 100% of potential users actually use that, and in the beginning it takes off very slowly, and then it increases, the speed of diffusion increases, and then finally the remainers also adopt. There are very famous empirical examples, and probably the most famous example is from and the earliest example from an economic study about diffusion of an innovation is the one from Zwieg-Rilchers, published already almost 70 years, or actually at least more than 60 years ago in the Econometrica. And this was a study about American farmers and whether they use hybrid seed. In German, it's Hybridgetreide. Okay, so this is just particularly seed which yields a high return. Okay. And what you see here, first of all, the hybrid seed, here it's a percent of total corn acreage planted with hybrid seed. You see the typically S-shape in Iowa farmers. You have some farmers doing that rather early and others doing it late, but you get these typically S-shaped. And what you see is that Iowa farmers started to adopt these hybrid seeds much earlier than Alabama farmers. then the question is, why is it so? Are Alabama farmers that more stupid, or in the terms of Schumpeter, more indolent or more ignorant? Okay, and actually, what Greeley has showed is no, we are not more stupid. Just the economic conditions are different. It's just due to different probabilities, and that explains why Alabama farmers adopt late. Not probabilities, but profitabilities, should that read, okay? It's just was just more profitable to implement hybrid seed in Iowa rather than in Alabama. Later than Iowa farmers, okay? It's economic variables which explain that, and not some kind of different kind of information or something like that. Okay, that's what I also have in these quotes in the notes. So this was the first study. The second study, and I want to give you an overview of many industries here. This from a article by Mansfield in 1968. He just looked into the diffusion curves for many different technologies, like here coke oven, like the diesel locomotive, the tin container, and so on. Whatever continuous annealing is, I think in German it's Wandglühanlage. I don't know what that is, but bituminous coal would be Fettkohle. So, but anyway, these are important innovations. And what you see is somehow it looks like an S, but what is more important in a sense is that you have some technologies which are adopted almost simultaneously, and others which take very long. Okay, and what of course we want also to explain is why there are these differences. And what is of course most important from the viewpoint of economics is something like market size, an important determinant, or is it competition? And I will get back to that probably only next week, but we will hopefully you keep that in mind, that you have these different diffusion curves for the different industries, which might look like rather different. What you see here is, in a sense, a more modern technology. Okay, it's just, I think it's, I put it in German here. It's just the installations of photovoltaics, of solar panels on German rooftops. And here you see this S-shaped shape. Okay, and you see it really increased a lot. This is in megawatt peak, so it's 45. Actually, it's 45 megawatt or 45,000 megawatt. Is that a lot? Do you have an idea? Actually, the maximum load we have in Germany, don't put the finger on that, but it's about between 80 and 90 gigawatt. That's in cold, dark January days when all factories run at full steam. Okay, and you see this is more than half of it. And the point is, if we have a nice sunny Sunday afternoon, we can, or our photovoltaic is might even be more than we actually use in terms, or can use in terms, or do use or do demand in terms of electricity consumption. So we have to put these photovoltaic installations even from the net. But what you see, and that's the important point, is our S-shaped diffusion curve. Okay, and this S-shaped diffusion curve also gives rise to a standard kind of new installations. That's how it looks like. What you see here is it goes up again. Of course, this is the yearly increase or the annual increase. It's determined pretty much by politics, but it's also determined by cost of these installations. Okay, and I think we will have, I don't know whether Max put that in the assignment, we will have an assignment where you really will be able to estimate the slope of such a diffusion curve for these solar panels, given what is called an epidemic approach, and which I hope to explain within the next 10 minutes or so. Okay, here's what you see, again, an S-shaped diffusion curve. You could also look into the adoption of smartphones and diffusion of smartphones and so on. Similar. Now, what we just saw was, in a sense, interfirm diffusion, because these solar panels are typically on different roofs. Okay, and now it also holds this diffusion pattern is sequential rather than simultaneous adoption. It also holds for intrafirm diffusion. Here, the example again from Mansfield, I think, is diesel locomotives. Actually, if you were to go to Vienna some 5 years ago, the trams, the Straßenbahnen, okay, the tramways were in part about 50 or 60 years old. whereas you at the same time some very new ones. So you see you at the same time, the same company employs both very old and very new technology. And that's what you see also here for several companies. It really took quite, for 10% of the company, it took more than 14 years to get from 10% of these locomotives to 90% of these locomotives. Of course, the alternative would be the steam engine, okay? Dampflok. And so what we are doing here, or what is the task for economists here? As you already saw, and what was the great achievement of Grealich's, he related this diffusion pattern to economic variables. He showed that diffusion and the speed of diffusion and who adopts a new technology depends on variables like the cost of the new technology and the profitability of the technology. So the task for economists is then to make models which explain the adoption behavior depending on these important economic variables such as costs and profitability. And of course, these models, partially theoretical models, they should be able to reproduce this empirical diffusion pattern. That is, they should come up with an S-shaped diffusion curve. Okay, so we have many different models and we will capture some of them. One is whether the information about the new technology is active or passive. Active would just mean you get the information only about the new technology, if you attend a trade fair, if you read trade journals and so on. Passive would be you're just a farmer in Ohio and you just look onto your neighbor's farms, and if you see, oh, there's hybrid seed there, that would be passive. You don't do anything, but you just see that by coincidence, okay? And there might be perfect information about the new technology. So do you know perfectly whether Windows 10 works perfect or whether Zoom is perfect? Or do you learn that over time? Only because you know many people are using that and therefore you can draw some conclusions. And the cost of adoptions might be constant over time, or in terms of the solar panels, they were heavily decreasing over time, as you will see in a few slides. And profits might be constant over time. Of course, we always have a time dimension here because this diffusion curve is a curve in time. And suppose you're a farmer, typically you won't be affected much by what your rival farmers do. But suppose you are some car manufacturers and all other car manufacturers implement lean production, or they put computer or robots into their assembly lines, then they will have a cost decrease. And that will probably lead to, if you don't do anything, it will lead to your profits being lower. The more people or the more rivals have adopted these new technologies, the lower will be your profit. Okay, of course, we can have identical homogeneous firms, or we can have heterogeneous firms which might differ in size and so on. And I don't go into details with respect to this disequilibrium models and so on. Okay, what I now want to do, and we are almost done, but I think it fits rather well into the Corona crisis. I want to present to you the so-called epidemic approach, which really originates from the study of the evolution of diseases. And here the disease is a new technology, like the new hybrid corn. And the infection means that you obtain sufficient information on the new technology so that it is adopted, okay? You learn just from, as a farmer somewhere in Ohio, you just learn about the new technology from what your other farmers do. So you have n potential users. Actually, in Germany, you would have 80 million people who can get COVID-19. Okay, but in terms of potential users, I don't know how many rooftops we have in Germany in terms of the which are possible or well equipped to have solar panels on them. And you have empty users at time. These are the infected in a sense, okay? The people who have a solar panel on their roof. And then you get some rate of infection. Actually, that's really closely related to our rate of infection. We have this with COVID-19 here. So what is a probability that you get informed about the new technology? Now, if there are, I now keep with the farmers, if there are M farmers, and a total number of n farmers. Suppose you have a total number of 1,000 farmers and 100 farmers use this, and it's just by coincidence that you meet one of these other 100 farmers. What is the probability that you meet one of the farmers who uses hybrid corn? Now, if it's 100 of 1,000, it's 10%. Okay, that you meet someone who uses hybrid corn. And what is the probability then that you are infected? This is just this beta parameter. So beta times the probability that you meet someone is the probability that you get informed or that you get infected. So if 10% of the population is infected, with COVID-19, and the chance that if you meet someone is 50%, so the beta is 50%. So if you just go around, the probability that the next guy who meet is infected is then, if it's 10%, would be 10%, okay, times 50% here would be 5% then. Okay, and then, therefore, you get some average number of newly informed potential users on this interval. So DMT is just a change in the number of users. This is the number of our new infections. And the number of new infections is just the probability that someone gets infected, okay? And who can get infected? Yeah, only the people who are not yet infected. So the total number of people who can become infected, the total number of forms we have, minus the number of forms who already use the new technology. And this is just a standard kind of differential equation, and this has this solution, okay? And this is alpha is a constant of integration, and the whole thing is a logistic curve. You know that I always use Mathematica, and if you use Mathematica, you put that in that differential equation here, okay, and tell Mathematica to solve this differential equation, and you say, okay, we have some guys, gamma, of course, in order to get an epidemic, you have to have some people who attracted it somewhere, even if it's from bats or from someone, you have to have some positive number, and if you have this number gamma, what you get, really, the solution Mathematica throws you out is this thing here. And if you plot this thing for certain parameters, so the total population is 100%, this beta is 10, the gamma, 2% of the population somehow autonomously contracted that, you see you get this wonderful S-shaped diffusion curve. Okay? Now, if you looked up very good, you will see that here we have a slightly different version of M. We have an alpha here, which we don't have here. We just now rearrange it up. Before I do that, I just want to show you how the infection rate affects this here. You see, if the infection rate beta is lower, that you really get infected, it will be more extended. Okay, it takes longer. It shifts out. Okay, that's why it's important to keep the infection rate down or up in terms of diffusion. In terms of the illness, it goes rather down. Now, here what I have here is just also depict the number of new infections. And why do I do this? Because, okay, remember a few slides ago, I showed you these two slides here. This is how it looks like for the solar panels. These are the cumulative installations. And here you see the new installations. This is this hump-shaped or inversely U-shaped curve here. And if we go back, you see that's what is really almost perfectly reproduced by this model. Okay, that's what this model reproduces. Okay, yeah. Now here, and I plotted this here. So and what I did here is remember what we had this alpha up there, and here you see you just use a certain definition of alpha. Here I use m over n. This is just the share of infected. Okay, and you get here our logistic curve. Why is that so interesting? If we rearrange that further, and here what we are doing here is the number of infected divided by the number of not yet infected, we get this e raised to the power of alpha plus t beta. Okay? Why is that interesting? Now, yeah, it's a perfect thing, because if we take the log of this, we get a linear equation. And if you have a linear equation and you have some data, we can just use OLS, ordinary least squares, and estimate that. And actually, that's what you are going, hopefully, Max should tell me if it's wrong, what you will do in the tutorial class, because there you see we have the data on the solar panel. So what you really can estimate there is really the speed, the beta of the diffusion, and this alpha. Okay, that's what we can do. And that's actually what Grilius did. And what Grilius did then was, first of all, estimating this parameter beta. And then, of course, he had only one parameter beta. He had a parameter beta for Kentucky, he had a parameter beta for Wisconsin, for Alabama, and so on. And then he ran a second regression where he tried to find out what the determinants of these betas are. Okay, and that's what we are turning to next. Why is it sensible to have this kind of approach? So why should the epidemic approach make sense? What is a mechanism which drives diffusion? I was telling you about an epidemic, about a an illness. Of course, that's different from the adoption or diffusion of a new technology. Why? How could we relate that to the adoption of the new technology? Actually, that's information. The more people are using, say, Windows 10, starting from a situation where everyone uses Windows 7 or even XP and so on, the more people there are, the better information you get about how good this technology works. And so what Mansfield wrote here, he just looks into the discrete change. Previously, note that we had a DM, continuous change. Here we have the discrete change in the number of users, of infected people. Here just normalized by the number of people who not yet have adopted a new technology. This is just a change, the discrete change from today to next year. Okay, and now again I have to erase this here. And now this change is a function of something. This change is a function what Mansfield called uncertainty. It's a function of profitability and it's a function of cost. That's what we mention here. And of course, more people will adopt the innovation if profits go up. That's our G2, the derivative of Z with respect to the second argument here. And if costs go up, fewer people will adopt the new technology. And if uncertainty increases, also fewer people will adopt the new technology. Okay, and what we are doing, or what Mansfield did, is what is uncertainty? And actually what Mansfield said, yeah, you get much less uncertainty if more people have adopted a new technology. Okay, so this is just a proxy for uncertainty. And you have to, of course, change your function now, because m over n now, if m increases, this just means a drop in uncertainty. Therefore, you would get a higher number of adopters. If you do some Taylor approximations, you can then have something on the logistic curve on this beta parameter, and you can estimate the betas as a function of these parameters. So the shape of the curve is a function of the economic variables, and that's what Griliches and Mansfield did in their study. The point is now, actually, I did what I wanted to do. I wanted to stop here anyway, but actually what I did, and if you have another 2 minutes, I would relate that to the current discussion about COVID-19, because actually what we see is we see a huge literature starting. Oh, the question is, do you give me another 2 minutes or 5 minutes even? Okay, so what I want to briefly look into, if I find it, is you see currently a huge number, a surge of papers which from economists which deal with COVID-19 and the welfare effects of reducing contagion. And what he does a so-called SIR model, which means susceptible, infected, and recovered. Actually, he adds a D to this model, death. Okay, and these models are very close, and you see also Darren Acemoglu has some papers on that, also doing such a model. And what they actually do is they use a variant or a derivation of this patent race model. And what I have to show you right now, of course, it's not a patent race model, but it's an adoption and diffusion model. Okay, so you see, shouldn't do the 2 chapters on one day. It's just how that looks like. And if I manage to move over to Mathematica, what you see here is this is just the equations. This is just the equations Pindyck uses, and you see these equations are pretty much the same equations as we have. This is just the number of susceptible. What is the difference with that model? Of course, in our model with the epidemic approach, here we have our number, if you can see that here, we have the number of newly infected, okay? And that's pretty much the same what we have here. He uses I for infections, and I is just a share, so it's something between 0 and 1. Or 0 and 100%. And here you see S is susceptible. That's the ones who can get the illness, okay? Because they are not yet infected. That's pretty much the S is just the N minus M here, okay? And the important difference with respect to COVID-19 is that you get something who recovers. And of course, that's nothing you have in the adoption literature, because here either you adopt, and once you have adopted, you keep this new technology, or you do not have adopted. If you attract, or if you get COVID-19, you might recover, or actually that's what's down here in the D in the last equation, you might die. Okay, and so here you have a point that some of the infected people recover. And because I ran out of time anyway right now, and it's rather late, I just want to show you that if you throw that into Mathematica, these slides, you get an awful, I did that on Sunday night, and you get some awful solution, and I didn't quite what to do with that, and I didn't have the time to look that up. But what you can do, and that's what I did, just use a numerical approach using Mathematica as a great software. You just throw that in, so these are just your differential equations I had in the very beginning. You use some starting or boundary conditions here. Okay, you start up with only one tenth of a percent is infected. No one did recover yet. I didn't account for deaths here because it's too complicated. Was too complicated. But what you see here, if you do that, you get here some numbers where you can see, of course, at the very beginning, 100% of the people are actually. I should use a nicer one, which produces other numbers. Here, at the beginning, 100% are susceptible. Then some get infected, many get infected, and some get then or recover then again. Okay. Now here we have actually what is a very interesting thing about Pindyck. He relates this beta parameter to the so-called reproduction rate, Reproduktionsrate. Okay, how many new people are infected by one newly infected. Moglu and also by Pindyck, what they do is they look into the effect of different lockdown policies. Okay, in the paper by Darren Atzemoglu, they look into the optimal lockdown or the optimal stay-at-home orders. Given that you have a certain infection rate, that you have a certain recovery rate, and so on. And what economists typically do is they use some value of the statistical life. And so, in a sense, they try to balance what we always do, how much should we risk in order to get our economy run again. Okay, so I cannot do more here on this issue. I just will stop here. Hopefully you nevertheless found that last part interesting. Of course, it's not relevant for the final exam, but hopefully you considered it interesting. And we will move on with our discussion and various different approaches to adoption and diffusion of new technology. I thank you for participating, and I will be available for a few more minutes on WebEx. Yeah, there were some problems with the stream. Actually, as I noticed that you only see part of the Mathematica output. I tried to start Mathematica, but that just is too much for my computer. It cannot run these complicated Mathematica formulas at the same time as it does OBS in order to stream. But anyway, so hopefully you got the idea. Actually, what I showed you were, and that's what you hopefully saw, were these diagrams. Okay. Actually, perhaps we should start, if you're interested in that, just apply them and start your own kind of calculations where you determine the different infection processes in the different countries. That's actually what all these people do who model the COVID-19 pandemic and who evaluate what is called NPIs, non-pharmaceutical interventions, how like curfews or mask wearing and so on, how they affect the infection process. That's what you would try to estimate based on such models. Okay, I took more time anyway, so I stop here and I'm available in WebEx for further discussions. And I, of course, apologize for any technical problems or the protection problems which arose. Bye.